Well, welcome everyone to today's webinar. My name is Giovanni, or if you probably have heard or talked to me. If you're a customer of NIRx, just call me Gio. I am the lead of the support team here at NIRx, and I am very, very happy to be hosting this webinar. But first, a few words about who we are. So we are NIRx, as you see, very big on the screen. NIRx is a provider of FNIR solutions since our inception, and we pride ourselves in providing very, very high quality FNIRS devices with the best data quality in the market to over 1,500 active end users worldwide. And we also pride ourselves in providing amazing support and a general platform. If you're curious to hear more about us or to hear what we're up to or see our educational videos, you can quickly go to our newsletter. If you're a digital recluse like me, who doesn't have any social media, you can still get stuff over email. So go ahead, get the QR codes to subscribe to the newsletter or follow us in any of your usual social media channels. Next slide, please. Or if you are already a customer and you have a question after this webinar, during this webinar, at any point in your life about anything, feel free to contact us in this support address and we will give our best to provide you with help. Be that with looking at data, getting your experiments up to speed, or general questions about FNIRs. Now, I am super happy to introduce my colleague who will actually present the webinar and not host the webinar. She will do the difficult part. My colleague Marina. Marina is our specialist when it comes to FNIRs in applications with other modalities such as fMRI or EEG or MEG. She has an extensive background in neuroimaging, mostly looking at neural networks in disease patients. She was formerly a PhD candidate at the Jülich Research Center, and now she's been a support consultant at NIRx for about a year and a half, I want to say. Maybe a bit more than that, but yeah, and I don't know if there are any more slides for me, but I feel
That's it.
like the stage is set. Marina, thank you so much, and take it away.
Wow, thank you very much for the very kind introduction, and thanks everyone for joining our webinar. This is again a refresher training of the Aurora data acquisition software. And before we dive into the existing and the new features in Aurora, I would just like to take a step back and look into the bigger picture of where this software belongs to. So Aurora that is the data acquisition software, which is part of the NIRS-Port2 platform, or the NIRS-Port2 ecosystem, as we like to call it. So our goal is to offer integrated solutions to our users that will allow them to create their own custom montage designs, acquire the data across different, not only in unimodal settings, but also multimodal settings. And this is why NIRS-Port2 offers the NIRSite software for montage design, of course, the Aurora software for data acquisition, which not only does standard data acquisition, but now also high density dot imaging. We also provide analysis softwares where you can take your acquired data set to perform FNIRS analysis. And of course, multimodality is now also possible with NIRS-Port2 thanks to the Borealis adapter solution, which allows to combine NIRS-Port2 measurements with fMRI and TMS measurements. It is also possible to combine your NIRS-Port2 FNIRS measurements with EEG, eye tracker, VR, and of course, we are very proud of our WINK solution that enables SPA FNIRS measurements using the physiological sensors. Our, as you know, detector bundles also can come with an accelerometer, which allows to also measure head measurements, which are very important when it comes to signal preprocessing. Now, As I already mentioned, this is a refresher training, so we do assume that many of you are already very well aware, knowledgeable, and are using our software and all its previous, not all, but some of its previous releases. We also like to emphasize the importance of keeping your software up to date. And if you are also subscribed to our newsletter, then you will receive notifications every time there is a new software update. And it is very simple. You simply need to go to our support page, help center page, to the software page, and there you can simply run the executable installation file, and it will already automatically update your current Aurora software as well as the related hyperscanning and NIRx converter solutions. So yeah, very, very important to keep those the software up to date, as each release comes with not only new features, but also relevant bug fixes. So yeah, keep your software up to date. We will talk about existing features. However, the main goal of today's webinar is to go over some of the new major software updates that have been introduced since our last webinar, which was already years ago. And I believe it was the 2021 release. So years later, we now have new amazing features that allow not only standard equidistant channel distance measurements, but also high density diffuse optical tomography features. And this is enabled thanks to the two main features, namely the multi-level illumination, the MLI. What it does essentially is that it allows to set a split ratio to group your channels into different groups based on their channel distances and introduce separate time steps for the source illumination of those groups. And finally, it will adjust the source brightness based on the channel group. We will go over these features, but this is just a general overview of what we will be discussing. The second feature is the enhanced frequency encoding, the EFE, and we are also going to look into how this feature, the benefits of the feature and how it can be enabled within Aurora. And finally, the smart spatial multiplexing has been introduced, replacing the bilateral illumination, again available in the illumination pattern menu in Aurora. A few small updates just to mention, the LSL trigger stream can now be continuously monitored on your Aurora taskbar, and another feature which is no longer new is the single device split hyperscanning option within the hyperscanning app. All right, so what makes Aurora so versatile between subjects and between environments is its source brightness optimization feature. So Aurora enables to increase the dynamic range of the signal quality by optimizing each individual source. And it is also optimizing it to consider factors such as interindividual differences, which are the skin variance in skin hair pigmentation, variance in optode coupling, how well the optode coupling is with the scalp, as well as considering the ambient light interference that can lead to saturation. And another major factor that the source optimization considers is the source detector distance, so the channel distance. And as we know from the Beer-Lambert law as well, is that the light intensity and the source detector distance have an exponential relationship, which means the signal intensity decreases exponentially as the distance increases. Another major feature that makes sure we avoid any crosstalk is the time multiplexing. So what time multiplexing, the standard time multiplexing means is that the sources are switched subsequently and not simultaneously. And in the case of a standard montage, so approximately equidistant channels, each illumination will be, each channel will create a unique timestamp. This means that the number of channels equals to the number of timestamps, and this means that it's also going to affect the sampling rate. So the more channels we have, the lower the sampling rate using the standard time multiplexing. And the way that Aurora quantifies the signal quality is done through the given 4 matrix, which you're already, I assume, well familiar with. It is the coefficient of variation, the signal level, dark noise, as well as source brightness. But let's just go over each feature quickly. So we know that the coefficient of variation is one of the important matrices we want to consider when doing our signal optimization. This is essentially the ratio of the standard deviation and the mean of our channels. So this ensures that we do not have channels that have very high variance compared to the other channels. And here we have our units in percentages and the different scales from excellent to too low. And as you know, we want to remain within the range of excellent to acceptable signal quality, as well as the channel variance. Moving on to the signal level, this is the second most important, so to say, metric that we want to look at before we start recording. And this is essentially the raw voltage that is captured per channel, per wavelength. And again, we want to remain within the excellent to acceptable range here. Right. So, and this was, again, we talked about the standard approximately equidistant 3 centimeter channel setup, which results in 2D data of our signal over the time. So we end up with 2D time series. However, another feature of NIRs that we can take advantage of is that going back to the relationship of light intensity and channel distance, source detector distance, is that by manipulating the distance and the channel density, we can also manipulate the cortical depth that is being measured, and essentially using high density, so increasing the number of channels, increasing the number of channel distances, we can obtain, we can go from the 2D time series to a 3D map of our cortical map. So what are the advantages of using high density dot measurements? The main advantage is, of course, the increased spatial resolution, as well as the increased lateral specificity. And again, of course, using high density measurements introduces several challenges, that being the increased number of overlapping channels and the need for good multiplexing and an increased high dynamic range. So, of course, high density comes with challenges and it comes with trade-offs that can be met through software solutions, and this is what we're going to look at today. So, as we mentioned, having variable channel distances, having shorter and longer distance channels means that we need a high dynamic range, because longer channels will require brighter sources, whereas using brighter sources will lead to saturation at shorter channels. So we want to be able to attenuate our signal brightness based on the channel distances. And this is exactly what is possible by the multi-level illumination feature. It will allow to adjust the illumination based on the channel distances. And the way this is achieved is that the source illumination is adjusted based on the channel distances and using separate time steps. So the downside of this, however, is that by increasing the time steps, we are trading off the sampling rate. So this will result in a reduced sampling rate. And Also increasing the number of channels, increasing the number of time steps is going to affect our sampling rate. And of course, another challenge of having more channels located close to each other is the increased risk of having crosstalk. And one solution to avoid the crosstalk and increase our sampling rate is the enhanced frequency encoding. This allows to illuminate sources simultaneously at different frequencies, ensuring that there is no crosstalk and there is reduced time steps, which means increased sampling rate. All right, so let's look at the first feature, the multi-level illumination. We already talked about how Aurora will automatically calibrate light sources for the best, most optimized dynamic range. And the way it is done for the standard, what I call equidistant channel montages, is that it will calibrate each source equally for the channels that are linked to that source. However, when we have multiple variable distances, then we want to make sure that, manipulate our source brightness for the shorter channels and for the longer channels differently, as is shown in the figure here. So the way that this is done by the multi-level illumination is that we can set a threshold that will separate our sources into longer and shorter channel groups, and we will have double the illumination of each source. So each source will be illuminated twice at different intensities for the first group versus the second group. And this will, as a result, lead to more optimized signal quality, despite the variable channel distances. Again, as I mentioned, there is a downside to this in that we are increasing the time steps, which means we are slowing down the data acquisition, which is going to result in slower sampling rate, reduced sampling rate. However, this can also be overcome by the next feature, the enhanced frequency encoding. So enhanced frequency encoding allows us to illuminate the sources that are located nearby simultaneously without causing crosstalk, and this is done by using unique frequency encoding. So, and you can see in this image on the right side, what is shown is 8 different emitter frequencies. This is possible by having up to 4 sources illuminated simultaneously at 2 different wavelengths. So currently you have the option of using from 2 up to 4 sources in enhanced frequency encoding. And we're going to look into this as we have prepared a short demo for you. So I'm going to show exactly how this feature can be enabled and what the different 2 compared to 4 settings look like. So the way to enable MLI is already done in your configuration. So where you define your configuration within Aurora, as we will see in a few minutes. So here you can define your split ratio. It will by default be at 2.0. However, we can manipulate it because depending on the number of channels that we have, we will need a different ratio. And here we just have an example of what it can look like. So if we have channels at 15 millimeter distances and 30 millimeter distances, and we have a split ratio of 2, this means that the 15 millimeter channel, which is half the distance of the 30 millimeter channel, will be put in a separate time step in the first group, and versus the 30 millimeter will be in the long channel group, and they will be illuminated at 2 unique time steps at 2 unique source brightnesses. So EFE, then the frequency encoding feature can later be edited in the configuration again. And here you have the option of using 2 sources or 4 sources. We can also adjust the frequency rate, simply adjust the sampling rate, but as we will see, it is indeed recommended to use the EFE when we're dealing with a high density montage. Finally, there is also the feature of smart optimization. The idea of this is to combine all the features into one. So this is like the quicker approach when you are not sure how to set your MLI and EFE features. And so it is combining all the features such as time multiplexing and frequency multiplexing, and adjusting for for a more optimized dynamic range. However, this feature should also be used with caution when considering the distances of the sources, so how close those sources are to each other. And as you will see in Aurora, it will show you a warning to consider the risk of having a crosstalk. So well, this feature sounds great, sounds very easy. It is also advised to always look into your channel distances manually before using the feature. Okay, so now, as I said, we have recorded a short demonstration of using Aurora to record a whole head montage of standard equal distances. So these are around 3 centimeter distances, as well as a high density montage. So I'm going to first show you first I'm going to show you the whole head example. So here we have a whole head montage which covers, all the brain regions at equal channel distances of approximately 30 millimeter. And here we are using 2 NIRx port 2s in a tandem mode. As you know, a single NIRx port 2 can host up to 16 sources and detectors. And if we want to have a whole head coverage, we need 32 sources, 32 detectors. This is possible in a tandem mode using a daisy chain to connect the 2 devices. Here we are also using our physiological sensors connected to the wings. We have connected the temperature sensor on the hand is being demonstrated. We have also connected the PPG sensor, which is right now being placed on our participant on the earlobe. And now we're going to look into the features within the software. We will switch to the software view. So as you're familiar already with the view, here we have our, at the very top, we have the options from left to right of selecting the devices, selecting the configurations. So right now we are on the selecting devices page. We have connected the device using the USB connection in this example. And as you could also see, because we have the wings connected, we also have the wings icon, which confirms that it is connected. Then on the right side, we also have all the information about the device. We can see how many devices are connected, and the wings which is being connected should also be shown. So nextly, we would want to choose our configuration if we already have one created, which in this case we did. So this is just an example of, sorry. Let me go back to the video. Okay, I'm going to go back to this view. I just wanted to highlight the different configurations that can be created. Okay, let me just pause here. Okay, so exactly. So if we are using a configuration for the first time, of course, we would want to create a new configuration. For this example, I already created my whole head configuration. We will go through the creating a configuration step in our next demo. And of course, I do have several random configurations here because I have been using so many by now. But just to scroll through a few of them, we have, for example, this high density montage of 48 by 64 sources by detectors configuration. We have a whole head, which is what we need to use for this example. And here we can also increase our sampling rate because with 32 by 32 configuration, the default sampling rate will be low. However, we can modulate it from the configuration. Now I'm going to test my LSL connection as well. So here we should get the confirmation that the LSL stream is good and running. Yes, so we have selected our configuration. We have modulated the frequency to 2 Hertz. And the next step is, of course, signal optimization. It's very important to perform signal optimization for each individual participant, considering the inter-individual differences, of course. And in this montage, we also have short channels, which you will see. You can see the short channels as they appear with the circle around the sources, as we have our short channels placed around the sources. In this case, we have 8 short channels. So you see that already without any manipulation, we have very good signal quality. Of course, this doesn't happen with every individual. In this case, we have a comparably easy participant. So I could already start recording. However, you see me moving the spring tops on the cap right now, trying to improve the signal even better. Of course, with more challenging hair, you would need to spend a little more time moving those spring tops. So we do advise doing this 90-degree movement of the spring tops. In some cases, you may want to change your spring tops to a higher intensity. So here we have spring tops varying from 1 to 3 with zeros in the front, in the prefrontal area. So this is what I'm doing right now, moving the spring tops, and already the signal is improved. Of course, we could spend some more minutes making sure that everything is green and we have an excellent signal. However, for the sake of the demonstration, we're testing how fast can we obtain good signal optimization and be ready to go. And you can see that within a few minutes, you already have sufficient data quality. So yeah, we did scroll through all the signal quality features. And now we are ready to start recording. Again, we have the different features for the monitoring our signal while recording. So of course, it's important to do the signal optimization. We have already talked about this. However, even throughout the measurements, it is good practice to keep monitoring the signal quality. Using the line plot is what we advise because this is the most informative way of viewing your channels. We have the 3D view. We can select the HPR or HPO separately. We also have the average block average view, which is not very useful in this case because we're not actually running a task. We're not using triggers at the moment. Here we can also calibrate our accelerometer if we're using one. In this case, we had several accelerometers, and it did take me a few minutes to find out which one was actually placed on the head. And this is exactly what's happening right now. So accelerometer number 4 was actually the correct one. which is what I needed to calibrate. And this 3D view is also very nicely showing how the accelerometer works across the axis. Back to the line plots. Again, important to look into the several features of what a good signal quality should look like. That is, you want to see the heart rate, this 1 Hertz activity that we see very nicely in this case. We also want to see slower drifts in the oxy and deoxy, which is linked to respiration. So these are a couple of physiological measures that we should be able to see if we have good optical contact in our channels. So in this case, yeah, here we can also clear the view. We can reset the baseline. We can have the hemoglobin concentration changes view as well as the raw signal. Now we are moving on to the biosignal view, and this is our wings data. So as you remember, we are using the temperature sensor as well as the PPG. So we have the heart rate, the PPG information, the oxygen saturation, as well as the temperature. In this case, where you see the temperature increasing, this is when we asked our participant to blow on their temperature sensor, so to increase the temperature. Yes. So this was the first example of a standard whole head imaging. And now the second example we have prepared is actually using a hybrid high density and a standard motor montage, which you will see in a minute. And here we are going to demonstrate how to enable the MLI and the EFE features. And we will look at the overall signal quality together. Again, we asked our participant to wear the now high density, what we call the hybrid cap. So on one side, we have a high density montage where you have sources and detectors at very close distances. And on the other side, the side that we're facing right now is the motor, is our standard motor montage, covering the primary motor cortex area. So this is not a montage, this is not a configuration you would normally use. This is something we have been using for the sake of comparison, to compare high density channels to standard channels. So normally you would likely have bilateral high density configuration. So again, we're using the wings sensors. Now we added the respiration belt as well. We added the temperature sensor. And I think in this case, we did not connect the PPG. So we're going to look at those two sensors. So what you see the participant doing in the beginning is this shimmying of the head, so holding the cap and shaking the head. And this we find to be very useful when improving the optical contact. So this really saves time instead of individually removing the hair away from the opto tips. This way, especially when you have the double tip optos, this really helps to move the hair away. So sort of the double tip of the optos actually serves as a sort of a comb to comb through the hair and move the hair away from the opto tip. So it really significantly reduces the preparation time. And again, we are already connected to our device. As you can see, two devices are connected, daisy chained, and we're scrolling through the configurations here. Because we need to enable the multi-level illumination, we're going to create a new configuration. And in this case, I need to select two devices, two 16 by 16. I'm selecting an accelerometer. If I were to use, so if, no, I clicked the wrong time point. I'm very sorry about this. Okay. we're back. Yeah, so if I were to use a Borealis, again, I would tick the Borealis box and I would need to specify the Borealis serial number, which is not what we're doing here, of course. This is why I'm going to erase it and tick the biosignals because we're using wings. And here we have to specify the multi-level illumination split ratio. So what you can see in yellow here is the number of sources that are going to be split into groups. So the current threshold, I'm modifying it, starting at 2. I also need to select the right montage file, modify the split ratio. So here we decided to go with a split ratio of 1.7, which selected 7 sources to be split into groups. And this is exactly how many sources I have on the high density part of the montage, of our hybrid montage. Okay, so now we have selected the configuration. We want to save the configuration, make sure it is selected. We can now edit it. Right, we can select the configuration, and at this point we have not yet enabled the enhanced frequency encoding. We only enabled the DMLI feature. So of course we need to run the signal optimization. We have simply put the cap on the participant, ask them to do the shimmy. We have not done any further signal optimization preparation so far. And already we have pretty good signal quality, mostly green. We still see a few red. Zooming into the high density part, we don't have problems on the standard part. The high density part, we have a few red channels, which is why I'm going to wiggle the spring tops, move the spring tops on the head, and you see as I'm touching the spring tops, the signal is improving. So here it's important to click on the refresh button to have the values being refreshed online as you are preparing the cap, as you are moving the optodes. And already we have mostly green and yellow channels. And at this point, again, for the sake of the demonstration, we wanted to see how fast we can have good signal. Of course, we could have spent a few more minutes making sure everything is green, and this is what we would advise users to do. Of course, it's definitely worth spending the extra minutes for the sake of having good channels. You don't want to lose any channels in your data preprocessing. And right, so overall, we're satisfied with the signal. With the dark noise, I have to say, because we were recording, we had this giant recording lamp shining on the cap, which is not what you are usually doing. So we do have a rather higher dark noise. So here in the time steps icon, I will pray that if I go back, it's not gonna, okay. Yeah, here we have the different time steps. And you see where we have our split, we did set our split ratio to split those 7 sources. So the split group is adding those time steps. So we have now +7 time steps in our recording cycle, right? And now we can also see how the channels have been split in the next icon, the splits. So we see the 2 groups here, the longer channels and the shorter channels being split into 2 groups. And now I am not satisfied with my sampling rate here because I did not enable the frequency encoding, which is why I can go back to my to edit my configuration, advanced parameters. Here I could simply adjust my sampling rate. However, this can lead to crosstalk, as we talked about. What I want to do is to enable the frequency encoding of, so here we have the view of the 2 sources compared to the 4. And yeah, there you go. We have reduced our time steps. We have increased the sampling rate. Double checking the LSL stream. I think it was checked in the previous recording, but this one we're doing it now. Okay. We have modified the configuration. Again, make sure you select the modified configuration. And since we have modified the configuration, we will recalibrate, rerun the signal optimization. And as you may know, the signal optimization time will also depend on the number of channels that you have. So the more channels you have, the longer it takes to do the signal optimization. And again, overall, good signal quality. We've already looked into the signal quality matrix. Now you can see the time steps being modified. You see that, for example, source 1, source 12, source 15 are being illuminated simultaneously at a given time step. So is source 269 and 2611, and so on. So you can check each time step in the time steps view. Now we have the splits view again. We've already seen this. Making sure everything is correct. Now, if you're not sure about your split ratio when creating your configuration, it's also a good idea to do the split, to define the configuration, go to your signal, check your signal quality, and then you can always go back and forth and modify your split ratio. So again, back to the data recording, the line plots. We're looking for a good signal shown by the heart rate activity, respiration activity. We want to see oxy having a much higher magnitude compared to deoxy. So overall, we have some nice channels here. Back to the topo plot view, where we can hover over a channel and see the line plot as well. We have the 3D view. Again, block averages is not informative for us here. We want to calibrate the accelerometer, add any descriptions for the given participant that are of relevance, and back to the biosignals. Again, as you remember, in this case, we had the temperature sensor and the respiration sensor. So here we can ignore the PPG for now. Again, the temperature increasing as we blow on the temperature sensor, increase the temperature there. And here we asked our participant to modify their breathing, to hold their breath, breathe out, and you see the temperature sensor reacting to those, the respiration sensor reacting to those changes. And yeah, this was it for the demonstration. So I hope this was so far informative. And of course, I am looking forward to answering your questions.
Hey, thanks a lot, Marina. It was very, very informative. A lot of things have changed since 2021, and I'm glad we did a webinar on it finally. Yeah, so I think at this point we have a few questions that people already asked during the registration process, but if anyone would like to ask questions right now, about software, about maybe there's something you want to achieve in the software that was not covered today, or that you want a quick walkthrough, we would be super happy to do that right now. It would even be helpful for other people watching the recording afterwards. So please speak up. And otherwise, we can move on to the questions that were already asked. So I'll give everyone 30 seconds. Feel free to unmute yourself if you want to, or even type on the chat. We will monitor things and then we can have Marina answer some questions. Maybe to warm up as people start to get a little bit less shy, I will pull the first question already, which is about how do we improve signal quality? That's a very broad question.
Yeah, that is of course a general question. And I would like to emphasize that we already have some very useful webinars on improving your signal quality when preparing the CAP, when preparing the setup. Make sure to check it out on our YouTube channel. And overall, when it comes to good signal quality, we want to emphasize how important the CAP preparation is. Is your CAP prepared well? Are you using cable trees? Are you using spring tops, considering your subject? So this will also vary between the subjects, considering their head shape, hair, and the spring top intensity to be used. With more challenging subjects, you may need to use a bit of water or gel, and in very rare cases, this can usually be avoided by good CAP preparation, making sure the cables are not being pulled, making sure, the spring tops are correct, and
Yeah, I
make
think
sure to keep the
maybe,
webinar.
general comment on that. There are multiple reasons, as Marina said, where signal quality can be suboptimal. So keeping an eye out on all these little things and getting some hands-on experience would be the best way to get around it. She showed a nice feature of Aurora, which is the real-time refresh of the metrics, of the signal quality metrics. So that is awesome. If you're troubleshooting in real time, you can see if whatever you're doing has a positive or negative impact on data quality. And to also mention, there is a secondary webinar that was presented this year or late last year, I will not remember, by an amazing group in the US. It's in our YouTube list. We will make sure to link it on this webinar's recording, about measuring F-NIRs in people with stylized and texturized hair, which comes with its own sets of challenges. So people with braids and more elaborate hairdos or dreadlocks and things like that. It's a group with some amazing work in this direction of inclusivity, which has been using the NIRx 2 to measure people with those types of hairdos. So yeah, there is a video about that somewhere in our YouTube, and someone will put it on this one.
Donna just put it. Thank you.
Yeah. Thank you, Donna. And yeah, the name of the researcher is Rachel Romeo, before I forget to give the proper credit. So yeah. Okay, moving on to the next question. We talked about calibration, we talked about signal quality. Maybe, how to check if the signal is good during the recording. So this is the same type of question, but maybe a little bit more specific to during the recording. So what if something happened and I think I lost signal quality during the recording? What should we do?
Yeah, this is why it's good to keep good practice to keep monitoring your signal. So we recommend keeping it on this line plot view to make sure you don't lose optical contact, or there is not too much motion causing motion artifacts. So in case of sometimes maybe the cap was moved or it's been dragged down or whatever, especially during mobile experiments. In case of an abrupt movement, you can always go back to your signal and make sure it didn't cause any abrupt changes, so no high frequency spikes in your signal, and that you still see those physiological components that I mentioned: heart rate, respiration. Is your oxy-deoxy ratio looking normal? So if you do notice early on that you're losing signal, I would say it's good to rerun your signal optimization, check the cap. Of course, there are ways around in your pre-processing, so you can always remove certain artifacts in your data pre-processing, but it's always good to make sure you have good quality data. As they say, trash in, trash out. Pre-processing can only improve your data so far. I think I'm going into a different topic now, but yeah, monitor your signal. If you have a loss of optical contact, I would say go back, recalibrate, check your cap instead of risking losing a good channel.
Good, very good. Thank you. We had a question on the chat sent on the private chat to me. Curious about adding triggers while collecting data. For a lot of our experiments, we run different tasks with multiple trials that often vary in duration. So what would be some suggestions or insights when it comes to that? Should we do start and stop times? Should we do just start? And
Oh, okay.
what exactly should be done and how?
Okay, so Aurora has the two features of including triggering. As you know, you can have the TTL triggers, you can have LSL triggers. Now, this question is more about experimental design, as I understand, how you want your triggers to be set. This is, of course, depends. Each experimental protocol is different. Usually, if you know your trial duration, your rest duration, you don't need an end trigger. It's enough to have a start trigger for your stimulus, then a start trigger from your rest, and the period from stimulus to rest is your trial duration. Yeah. Am I answering the question?
Yeah, I think so. I think maybe the other dimension of the question is the how. So if you're just looking into options, I think the two most straightforward options would be to either use the manual triggers, which I don't recommend at all because this is error prone and not really scientific. Or you could look into a software tool that will manage your triggers for you. So for example, if you want to use the lab streaming layer, you can use CyclePy. It's very well integrated with that, very simple to use. A lot of examples online, especially if you already program in Python or have someone in the lab that does it. Second option would be to go something like ePrime, which is, well, for some people, it's the easier tool to use because they already have it in the lab, they already are familiar with it, but it also streamlines a lot in terms of data acquisition because NIRx has a ePrime extension. So basically, you buy ePrime, you get your little NIRx package, and you can control the acquisition all from ePrime. So you don't have to worry too much about controlling things also in Aurora. So that's another option. I have the email, the person that asked the question, I'll make sure to follow up, but I'll also put all this material, like our guides to using triggers and about the ePrime extension. I'll make sure that my team puts it in the YouTube link to this webinar afterwards. Thanks for the question. Okay. Oh, wow. Yeah. Thanks, Mahipan. Well, people are lightning fast with these.
Yeah.
I have another question here from the pre-asked questions. What is the usual channel distances in DOT with NIRx? what are the considerations for split ratios and what is the maximum DOT coverage? Okay, I think I can take this one, Marina. So channel distances in DOT with NIRx, you're limited by the basically the physical size of the optode. So you could have your lowest distance be the short channel, and then you would have an 8 mm channel. That's not usually what people are doing with high density. They go for the first channel already having some brain information on the first distance. So if you're doing it like others in the literature, like the Joe Culver group or the David Boas group, you want to go for not using the short distance channels as we have implemented them. And then you're looking at distances such as 16 millimeters, 35 millimeters, and 40-ish millimeters as the three neighbors. So this would be, not the actual distances, but the usual distances that you would have in a high density patch with NIRx optodes. Then split ratios. So you have a choice, right, of how to split your multi-level illumination. And this comes to this single number, the split ratio number, in which you choose, okay, my lowest distance is 16 millimeters. If I want the 16 millimeters to be separate from the 35 millimeters, I need to make sure that 16 times my split ratio is lower than 35. This is getting a bit technical, but if you open up the manual or if you just try it for yourself a little bit, you will see how Aurora splits your montage differently, and it's very visual. Once you select a configuration, you can see the time splits or the illumination splits as Marina showed in the video. And then last thing, sorry, maximum DOT coverage the NIRx 2 can offer. Honestly, I don't know. The most we've tried at the office and succeeded with was 5 devices, so 80 sources and 80 detectors, which is quite a lot. If you try to put all of that in the head, it starts looking very crowded. It works, but it looks very crowded. So that would be my answer for now. If you want to try with 6 devices, be my guest. It will probably work, but it will also be, I don't know where you're going to put all those optodes. Cool. I see that we are almost on time. So if there are any final burning questions, please ask them now or remain silent forever. No, you can ask them afterwards to support@nirx.net or at any time if you ever see us around, or even on the comments of the YouTube video. Oh, Kat wants to join the webinar. Okay, then people, thank you so much for attending. Marina, thank you so much for presenting, and
Thank
we'll
you.
see you in the next one. Don't forget to like and subscribe. Goodbye.